All right, thanks for coming. I'm going to tell you a little bit about the second homotopy group, pi2 of x, in classical and digital topology. This is kind of a more accessible version of my talk that I'm going to give at the joint meetings in a couple months. And it's based on a paper that we worked on this past summer called the Second Homotopy Group for Digital Images with Greg Lupton, Oleg Musin, Nick Scoville, and Jonathan Trevino. And you can see the paper on the archive now, although it's a little technical, but probably can understand it if you really wanted to. Although I don't necessarily recommend it. I want to try and give you a feel for what the paper's all about and what you can find in there. So let's talk about the second homotopy group of a space. This is kind of it's a classical kind of topology thing that was done in the early 20th century, I guess. It is a generalized version of the fundamental group, which a lot more people are familiar with. So it's written as pi2 of x. The fundamental group is pi1 of x. The pi2 is a higher dimensional version of the fundamental group. So maybe I'll just remind you briefly about the fundamental group. This is a typical thing. I think everybody in grad school learns about the fundamental group. Not everybody learns about the higher homotopy groups. The fundamental group, so it measures how many holes there are in your space X using sort of shrinkable loops. It's kind of like imagining what are all the different ways I could, say, put a rubber band into the space and see if it loops around some holes in the space. That's what the fundamental group is meant to measure. What are the holes? For example, if this is your topological space, it has 3 holes in it, right? According to the fundamental group, those 3 holes can be measured sort of like this by imagining you could wrap something around. You could go around this hole or this hole or this hole. So the fundamental group in this case has 3 different generators. It is a group on those 3 generators. So it's a group. The group operation is like, well, I could go around this one, or I could go around this one backwards. That would be the inverse. Or I could go around this one followed by this one. That's the group operation. Is you go this and then you do this. So that's how it makes a group. In this case, it's a free group with 3 generators, and the 3 generators are represented by these 3 loops. All right. Now, what about pi2 of x? This is meant to be the same idea, but everything 1 dimension higher. So I'll try to explain what I mean by that. 1 dimension higher for everything. So this, instead of putting like a rubber band in your space, it's more like putting a stretchy balloon into the space and see if the balloon loops around any holes. So for example, if you do this pi2 of R3, that is the 3-dimensional space, then that's nothing because there are no holes, and so any balloon in R3 can automatically shrink down to a point. So pi2 of R3 is trivial because there are no holes in R3. But if I remove the origin, then this is not trivial anymore because it is possible to wrap a balloon so that it will like snag on the origin if the origin is removed from the space. All right. That's the idea. Now, for the rest of what I'm going to say, I'm just going to talk about pi2 of S2, where S2 is the sphere. This is the 2-dimensional sphere, which sort of lives inside of R3, if you want to look at it according to this kind of a picture. This is an empty sphere. I mean, the sphere it's not like a solid ball. It's just sort of a shell. All right. If it were a solid ball, then you could shrink a balloon down inside the sphere to nothing. But I don't want that. I want just the outer layer of the sphere. All right. How many ways can you wrap a balloon around the sphere? That's really what I'm talking about if I ask you what is pi2 of S2. And remember, this is all topological. So the balloon you imagine the balloon is stretchy, and also the sphere itself can be stretchy. I'm not just talking about a perfectly round sphere, but anything which is topologically the same as the sphere. I thought I'd do a little real-world example. You can try this at home with the kids. All right, here I have a potato, which is going to be my stand-in for the sphere. It's not perfectly round, but it doesn't matter. It's topologically a sphere. And then the balloon is represented by this vegetable bag that I have. And the question is just how many ways are there that I could like wrap up the potato with the bag? And here's the standard way to do it. You put the potato in the bag like that, and then kind of do that, and now it's wrapped up. All right, so that's one way to wrap up the sphere using a bag or a balloon or something. There you go. I tried to like crunch all the rest of the bag down to a point in my hand there so that it wasn't just hanging over. All right, that's one way that you could wrap the bag around the sphere. I also could have wrapped it up inside out, and according to the definitions of the fundamental group, that counts as being different from wrapping it around the right way. Now the bag I used looks the same inside out and right way around, but if it was like the inside and the outside had two different colors or something, you could tell it's different to wrap it up inside out. All right, so technically what we're talking about here is pi2 of S2 is the set of all continuous maps S2 to S2, where the first S2 represents like the bag or the balloon, and then you look at what are all the different ways I could sort of continuously wrap around this balloon and cover up the potato with it. So the domain S2 is like the bag, and the codomain S2 is like the potato. And this says modulo based homotopy. This is a little technical, but this is just the standard topological version of stretching and deforming a function. So in topology, you imagine that all of your spaces, the balloon and the potato, they're all sort of stretchy. You can move them around like that. You can't cut or break them. And we also imagine the functions are sort of stretchable functions. All right, that means two functions which more or less do the same thing in terms of going around are considered to be the same. But going around inside out, that's different from just going around the standard way. All right. This, though, is a little hard to get a handle on, the set of all maps modulo base homotopy. What I just said before, imagining like stretchable functions. There's actually a better way to visualize it, which is a lot clearer in my opinion. Rather than the bag or the balloon that we shove the potato into, I'm going to imagine it like sort of the napkin here, and I'm going to just wrap up the potato. It's the same thing, it's just visualized slightly differently topologically. So the standard way to wrap up the potato with the napkin would be like this. I do a little of this, a little of this. There you go, it's wrapped up. All right, that's one way to wrap up the potato with the napkin. We can wrap it around however you like, but notice in order for this to be like a legal wrap up, the points around the edge of the napkin must eventually get crunched down to a single point. Like right here, I sort of bunched up the rest of the points. And the rest of the points are the ones that used to be around the edge, right? Those are the ones that get bundled up at the end. That's what it takes to be like a legal sort of wrap up, all right? So I'm going to indicate that like this on my picture. This sort of red border means all of those points around the border must end up crunched down to a single point when I'm done wrapping it up. All right. All the red stuff must crunch down to a point. And now that we have that kind of way of thinking about it, you can just visualize everything on a flat surface. I'm not even going to put the potato in there anymore. I'm going to visualize everything. You can do whatever you want in here as long as it's continuous. You don't rip the napkin or anything. But it's just all this stuff around the outside has to go down to a single point. Now I'm going to indicate the standard way of wrapping it up. I'm going to draw like this. So this sort of spinny thing is not meant to indicate that I'm rotating the napkin. This is just like a right-hand rule kind of thing to say this represents wrapping it around this way rather than inside out. All right, so this is the standard wrap up. You could also do inside out, which I'm going to indicate like that, where the curly thing is going around the other direction. All right. You could also wrap it up twice. So there's more than one way to do this. It's not just the normal way or the inside out way. You could also do something like this. This means you wrap it up twice. This would look something like this. I go on just using the left side, I'm going to wrap it up first in the normal way. And then I take that little wrapped up bundle and I put it over on the other side and wrap it up again. All right. This is sort of a double wrap up. All right. So that's another way that you could wrap up the potato. And in fact, this kind of diagram, you can see easily that this is going to make a group. How would you imagine now that F and G are any kind of strategy for wrapping up the potato? You can add them together in this way. So if I know how to wrap up in some way and some other way, you can just do the first thing sort of on the left side of the napkin and then do the second thing on the right side of the napkin. Now with a real napkin, you might run out of napkin area, but remember this is topology, so we imagine you could just stretch the napkin out if you like before you do this more complicated thing. All right, and this is what makes this pi2 into a group. You do one thing on one half of the napkin and another thing on the other half of the napkin. And this is the group operation, all right? This right here is the group identity element. This would represent a wrap up, kind of in quotes, wrap. You're not really wrapping anything up. You just crunch the whole napkin down to a point without going around the potato at all, all right? But that makes an identity element because if I add this to this, it makes that, according to what I just said. But that, you know, topologically speaking, you can just stretch the f out here and you get what you started with. All right, this is a based homotopy of the function, which is a stretching. So that's the identity. That's what the group element looks. The group identity element looks like. It's just a constant. All right. What about inverses? This is a little harder to see, and I don't want to really get into the details. But it turns out if you start with a function over here, and whatever your strategy was, you just reflect it in one of the axes here. I did a horizontal reflection, but it actually works vertically too if you want. It turns out that these two things can be kind of smoothed out or joined together, and they will cancel each other out. Like I said, this is a little more complicated to see, but it's true. This of course is necessary for it to be a group, but this is how you do inverses in this group. All right. And one very interesting thing, and this is actually a general property of pi2, which is not true of pi1. It's also abelian. Remember, that means that it's like commutative. The operation is commutative. F plus g is the same as g plus f. How do you see that? Well, if I start with f plus g right there, remember I can like stretch and bend these things around. So I'm going to first just stretch them down so that they only are doing stuff on the lower half. All right. And now you do, if you ever see like topologists talking about this, why is the higher homotopy groups abelian? They will probably do something like this with their hands. It's like boom, boom, boom. This kind of a thing. That's what I'm going to do. So now we can move the g upwards just by, that's another one of these basic homotopy moves. You're just stretching. You're not really rearranging the topological properties. And now I can move them both like this, sideways. So I move the g to the left and the f to the right. And now you can probably see I'm going to move the g back down and then stretch them both back up. And I end up with g, oops, this is, come on now. There. This is g plus f. I started with f plus g. It's equal to g plus f. So this is why these higher homotopy groups are always abelian. The pi1 is like special in this way. The pi1 is not always abelian. All right. So what is this as a group? That's really my main thing that I'm trying to talk about here. What exactly is pi2 of S2? Well, it involves, so it has this. This is one way. The question is really just, what are all the different ways I could wrap up the potato with the napkin? You could do it like this. You could do it like this. This would be like one normal way of wrapping, or you could do the normal wrap twice, or you could go inside out the other way, or you could go inside out twice. But it's really just, you could do some number of sort of positive wraps or some number of negative wraps. All right, and it turns out those are the only possibilities. There is not some other like secret wild way of wrapping up the potato that's not covered by these possibilities. There's no other wacky way to do it. All right, there are no other wild maps of S2 into S2. And so for this reason, you know, all you can do is just the normal wrapping some amount of times. You could do it 2 times or 3 times, or you could go the other way. Inside out would be like -2 times or -3 times. All right. And that's why pi2 of S2 is isomorphic to the group of integers. It's just some amount of times, either the one way around or the opposite way around. All right, this is the classical result. Now, I said this, there are no other wild maps of S2 into S2. That actually requires quite a bit of justification, topologically speaking, and it requires that you understand really well all possible ways of mapping a sphere into another sphere, and this is not really an obvious thing. I mean, it was worked out a long time ago. I believe this basic concept was known to Hopf, say, like in the 1920s. So it's been around for a while, but it's not something that it requires some real work to get to that. And if you change these 2's around, Hopf actually understood pretty well Sn into Sn, but if you want to do, like, for instance, S3 into S2, there actually are other wild ways to do it. So this is an interesting thing, and I'm not really going to get into the details. All right. Anyway, all of that was the classical topological picture that people have been talking about for a very long time. I want to talk about digital, and this is what the paper with those other guys that I said at the beginning, this is what the paper is all about. Try to do the same thing, but for digital spaces. Let's see what I mean by that. What I mean by digital is we're going to look at so-called digital sets rather than smooth shapes, all right? And this is part of, it's a fairly new discipline called digital topology, and the idea is geometry and topology of smooth shapes has been around for a very long time. Although in our world the way it is now, it is important to analyze digital type shapes. And, do they behave in the same way? The answer is, yeah, kind of. Like a lot of the things that are true of ordinary smooth geometric shapes are also true of digital type shapes. I mean, things that are like made out of pixels. But some things are different. So that's we're trying to figure all this stuff out. So I am no longer talking about a smooth, round sphere like that. I'm talking about some kind of like digital version of the sphere, which I guess would look something like this, some kind of like Minecraft or Lego version of whatever shape you want to talk about. And now, can we do all that same stuff in this realm, the digital setting? Does it still work? Are you still going to get, z for whatever the pi 2 of this is? That's what I'm getting to. So we're going to assume that our shape is made of finitely many indivisible pixels, and that's really the big difference. Is that there are finitely many pixels, and they cannot be. They are what they are. You can't talk about half of a pixel or something. We assume that the pixels are like atomic and indivisible, because it's a very basic property of classical geometries that you can always, like, if you have a line, you can always zoom into the line, scale it up in a smooth way. But this is not possible for digital objects. All right. So there are many approaches to digital topology. Our approach that we're going to use here is based on an approach that started in the 80s with the work of Rosenfeld, and then was developed into a more sophisticated topological theory by people like Boxer in the late 90s and then since then. So we're going to view this object, this digital thing, like a graph. This is the basic beginning of this theory. A graph meaning it's made up of individual points which represent the pixels, and then those points are connected by edges to some other points which they are next to. All right, so here's an example. This is sort of a graph theory version of this shape here. I turned it into a graph. All right, now that, as far as graphs goes, that is a very big and kind of complicated graph. I don't really want to talk about this graph because it has so many vertices, and if you think about it, was there anything special about that sphere in particular? Like, I could have made a bigger sphere, and it would actually, as a graph, look completely different. It would have more pixels and in a different arrangement, perhaps. So this is big and complicated. We're actually not going to talk about this graph here. It's far more convenient to use simpler representations of S2, and one common one that you'll see used in papers about this is just a rectangular box. Now, this doesn't look like a sphere to an ordinary person. That's not a sphere, that's a box. But topologically speaking, it should have all the same topological properties as a sphere, because it is, topologically the same as a sphere. So this is a common thing that people use as a digital stand-in for the sphere. It's not round in the same way, but we don't care about that topologically. We're actually going to go with this octahedral thing. This turns out to be the smallest possible kind of sphere-like thing if you want to do this digital type stuff. So this is an octahedron, and it's actually very convenient to represent this inside of R3. You can represent this as just the 3 basis vectors together with their inverses. So this is like E1 is the first basis vector E2, E3. If you think of these points in this way, you'll realize that the origin is missing here, right? There is a point at the origin, but I'm not including it in this. So this sort of octahedral object actually does surround some empty space, and that's what the sphere is all about. So this turns out this is the simplest and most convenient model to use of the two-dimensional sphere for us. All right, the zero in the middle is missing. I said that. So what are we talking about here? You want to think just like before about like the napkin wrapping around the potato. In this case, the napkin also is a digital thing, and I'm going to represent that as this sort of flat rectangle. The lines that you see there are just saying which points are next to each other. We are going to use diagonal adjacencies here, which makes it actually makes a big difference. That's a choice that people make here. But anyway, the important thing about these functions, wrapping up the potato here, is that all the points around the boundary have to eventually crunch down to a single point, and it might as well be the point at the bottom. So these are the types of functions that we're going to look at. Any function from a rectangle, now it could be a small rectangle or a big rectangle, but it has to be some rectangle where all the boundary maps down to the south pole here. And I'm always going to use this specific graph. The rectangle might be bigger or smaller, but this, where it maps into, this is always going to be this just 6-point octahedral graph. All right. These functions that we're considering have to be continuous. That is the basic topological property. What does continuous mean in this setting? It means that adjacent points on the left side map over to adjacent or equal points on the right-hand side. So if 2 points are next to each other, like connected by an edge in this graph, then those 2 points either go somewhere connected by an edge or they go down to the same point. This is almost a graph homomorphism, although graph homomorphism is required to take edges into edges. If you want to view this in purely graph theoretic terms, you can say the functions I'm considering are graph homomorphisms if I assume that if this graph is also a reflexive graph, if I also insert looped edges everywhere, then what I'm talking about is exactly the same as this. All right. So a typical continuous map in this setting would look something like this. I'm going to use colors for the rest of the time here. So these points around the edge all go to the bottom, and then I labeled by colors here where those points go over here. All right. It must have dark red along the outside in order for it to be a valid like wrapping up. And no color is adjacent to its opposite. So I labeled the colors over here in a slightly careful way so that the dark blue is opposite the light blue, the dark red is opposite the light red, and the black is opposite the white. What that means is you're not allowed to have 2 points over here which are next to each other, but they map to points which are not next to each other over here. Which means on this picture over here, you can never have a black next to a white or a dark blue next to a light blue. It doesn't happen. If that were the case, then this would be an illegal function because it's not continuous. All right. So that function, actually, I'm not going to be drawing graphs anymore. I think it's actually easier to just visualize as sort of ordinary looking pixels here. So that same function can be represented just like this. On the outside, you see the red, the dark reds, and then everything else can be whatever it wants to be. It's just you can never have, a black next to a white or a dark blue next to a light blue or a pink next to a red. All right. That's what I just said. No color is adjacent to its opposite color. All right, how do we make sense of the homotopy? Now, classically, this just means you kind of stretch your function out. How can you do that in the digital setting? This is actually a major concern because even these pixels don't stretch, right? You could add on a new column of pixels, but you can't stretch them out in a continuous way. So this is something we need to talk seriously about. How do you do a homotopy? This is the stretching and deforming operation classically, but you can't really stretch in this setting. So there are 2 basic operations, and this is inspired by Boxer's original treatment of the digital fundamental group. One is called a trivial extension, and that just means you add on extra rows and columns to your diagram and just make them all this dark red, all right? You can't stretch this diagram. The original diagram, you can't really stretch it out because pixels are not stretchy. But you could just add on extra dark red pixels. So this counts as a legal operation to change one function into another. These two things, they still topologically represent the same function. The other move is a little more complicated, and that's what they call spider move homotopies, or point-by-point homotopies. So this function over here is considered to be equivalent to this function over here. You might not be able to tell the difference, but what the difference is right here. See, this pixel, which is a white, has turned into a dark blue. This is, you are allowed to change a function one point at a time. And the rule about how exactly can you change it, actually in this setting you can change it however you like. It's just that this point here, because it's next to these dark reds, you can't change that into a pink. But if you want to, you can change it into a dark blue. You also could not change it into a black, because a black, if you make this a black, it'll end up next to a white, and that's not allowed. So these are changing one point at a time, which in the literature there's some graph theory papers that do very similar stuff to this digital topology, and they call this this type of move a spider move. I actually, a few years ago I wrote a paper where I called this a punctuated homotopy, which I thought was very sort of highfalutin language. Punctuated meaning like one point at a time. I think spider move is a little cooler. In the literature, what I'm talking about here is sometimes referred to as a NP2 homotopy. There are a few different types of homotopies that are discussed. This is sometimes called a strong homotopy, or the categorical homotopy, or often just referred to as homotopy. If you want to, some papers will just begin by saying all our homotopies are this type, and then so we're just going to call it homotopy. But when you see the word homotopy in digital topology, you better be sure exactly what kind of homotopy are they talking about. This one that I'm talking about here, based on spider moves, is different from the NP1 homotopy, which is also known as the box homotopy. This is commonly used in a graph theory discipline called A theory, which, if you know A theory, you probably are looking at this and saying, isn't this just the same as A theory? It's not quite the same. There's also the discipline which produced this sort of spider move type paper is sometimes called cross homotopy theory. That is a lot closer to what I'm talking about. Anyway, I'm doing the categorical homotopy, or the cross homotopy, not the box homotopy. Unfortunately, the box homotopy is also sometimes called just homotopy. It's a little confusing. Anyway, using only these two types of move, there's the trivial extension where you just make the box bigger and fill in dark reds everywhere, and then there's this point-by-point spider move. You can actually do a lot with only those two simple moves. For example, you can do what we call a column duplication. Check it out. Here's, I'm going to start with that same picture again, and my goal is to duplicate the final column, like repeat the last column. Here's how you can do it. First of all, I extend the box by filling in reds. That was one of our legal moves. And then I'm going to, just using spider moves one point at a time, I'm just going to copy this column one by one into these positions. So first I copy the black over one spot, then I copy this blue over here, and then I'm going to copy the next blue over, and then the white over. All right. And so I have duplicated the last column by a sequence of spider moves. It's pretty simple, I think. That's a column duplication. Check it out. It's not only the last column you can duplicate. I could duplicate one of the columns in the middle. For example, if I start with this, and then first of all, by what I just did, you can duplicate the last column, right? But now what you can do is I could actually copy this sort of third to last column over by one position, point by point. That would look like, they already match up here, but I can copy the pink over here. I can now copy this white over here, right? And then actually, I guess I'm done here. So now what I've done from this picture, it's the same as the original picture, but I've now duplicated the second to last column. All right, so in this way, by doing these point by point spider moves, you can actually duplicate any column that you like. Now you have to check that those moves are always, they are guaranteed to be legal. Like doing this kind of operation can never produce, say, a dark blue next to a light blue, but it's true. All right, you can duplicate any of the columns. Here, by doing this same procedure over and over again, I duplicated here this second column now. And in fact, and this is actually important, you can actually go sort of take this to its ultimate conclusion. You can duplicate the leftmost column, which would look like that, all right? What's interesting about duplicating the leftmost column is basically what you've done to go from here to here is I moved the entire block by one position to the right. And this is very useful if you want to do this in larger pictures. What it means is if you have sort of a big sea of the red points and some little isolated block of stuff, you can move that block around however you like. You can move it to the right, to the left. You can go up and down by duplicating rows instead of columns. It works all exactly the same way. All right. We can translate any island. Remember, our only fundamental operation is moving one point at a time. But this certainly looks like I'm moving more than one point at a time. But it can be realized by moving one point at a time. All right. Great. And this actually is enough to make a definition for this group pi2 of x. So how do you add together two functions? You stick them next to each other. And it is still going to be an abelian group because this business, remember this business I was doing before, if you have two different blocks which represent two different functions which you've just added together, you can migrate them up and down and left and right, and you can move them around into their sort of opposite position. You can commute them. So it is an abelian group, which is quite nice. All right. There is one more simple trick that we can do by combining spider moves, and this is what we call the fill operation. It's just like the old paint bucket from your old, Photoshop or whatever. The fill. What this means is you just change all the values everywhere to something else. So here is an example of filling with the dark red, and all it means is you just change everything to a dark red, except for the ones which are not allowed to become a dark red. So in this case, filling with the dark red turns this picture into this one, and all it is you just change everything to this color, the dark red, but there are some points which are not allowed to become dark red because they're next to pinks, and remember, a dark red can never be next to a pink. So filling with red means change everything to a red which could possibly become red without violating the continuity. All right. You can fill with the red. You could also fill with other colors. Changes all pixels to red whenever possible. All right. We can fill with other colors. So in this particular example, filling with white gives you this picture. Now it has to, all of these functions, they must use the dark reds all around the border. So when you fill the picture, you don't change those ever. You change everything else. In this case, change everything else to a white, as long as it's not next to a black. So that's why these guys down here change to whites. These ones do not change to white because they're next to blacks. All right. If you fill with black, you get this picture here. Everything becomes black except for the ones which were next to whites. And if you fill with pinks, you get this picture here. Everything becomes pink except for the ones which were next to reds. All right. This is how the fill operation works. And this too is achievable by these point-by-point moves. Actually, how would you go from here to here, just changing one point at a time? Well, all those points you change to white, you have to check some details, but actually you can just change them one at a time to white, and everything works out just fine. So this is how the fill is also achievable by those single-point spider move changes. All right. Anyway, here's the big theorem for the paper. Sorry, there's a typo here. That should just be Z, not Z2. Pi2 of S2 is Z. It's exactly like the classical setting. There is basically only one way to do it. You could wrap the thing up one way, or you could go backwards, inside out, or you could do the standard wrap twice or three times or whatever. It's Z, not Z2, sorry. In order to make this work, we need to sort of create some standard functions that are analogous to these. Remember, the reason, classically speaking, the reason why it's Z is because every way you could wrap the potato is actually realizable by just doing some amount of these or some amount of these. This is like a positive one. This is like a negative one. All right. So what we would like to do in this digital setting is come up with some standard sort of simplest kinds of functions, and then say all possible functions can be expressed by these simple ones. So that would be analogous to these guys here. All right. And this is not rocket science. You could probably come up with the same thing if you thought about it for a few minutes. The simplest versions of these functions in our digital setting, they would look like this. So this one we call t. This one is a constant map, so we call it c. And then this one we call t inverse because it turns out to be the inverse of t. And you'll notice that this is actually a horizontal reflection of this one here. So we actually proved that t plus t inverse is a constant. That is, if you stick this picture right next to this picture, then actually you can change it point by point and turn it all into all reds. This requires some, it's like detailed pictures that show you can do that, but you can do that. You could figure it out too if you liked. All right, and we also proved that any old 5 by 5 square can be transformed into one of these. So this T is fairly specific. These two whites, these two light blues, these two blacks, these two dark blues. But actually, and you could imagine, what if I like rotated this picture or arranged them slightly differently? There are other ways you could arrange it, but actually, if you start with any 5 by 5 square, you can do your point by point moves to change it into one of these three. So it's good enough as far as 5 by 5 squares. Everything is going to look like one of those. All right. The big question is to show that, my goal is to show that basically these are the only things you can do, although you could add them together and get other more complicated things. The big question is we have to show that any big weird picture can somehow be transformed into these t's and t inverses. For example, like if I just start with something like this, can you show me how to make your little point by point moves to transform this into a bunch of t's and t inverses? That's what would be necessary. If it's really true that any picture like this can be expressed as t's and t inverses, then that means that this group is the same as z. We have to rule out the possibility that there's some kind of wild or crazy way of doing a picture like this which is not equivalent to the t's and t inverses. All right, so if this is what we start with, we must use our specific moves to turn this wild thing into just a bunch of those. And if that's possible, then we will have proven that the group is isomorphic to Z. All right? It turns out it is possible. We're going to do some sort of magical tricks here. And actually what I'm about to show you was discovered by just kind of playing around with examples of this on the computer. When I'm doing this kind of research, I often like to write some algorithms to do various things with it on the computer. Usually it doesn't really help to prove the theorems, but it's just kind of for my own sanity or to help me get a handle on things. But in this case, actually, I discovered, or we discovered something that at least I was not expecting. It turns out some sweet tricks, which we just kind of stumbled into. So the first thing we're going to do is subdivide the picture. This is a bit of a technicality step, but it is necessary. You start with this picture, and I'm going to just subdivide here by duplicating every row and every column 5 times. Remember, we are allowed to duplicate a row or a column, and if you duplicate every row and every column, what you get is basically a zoomed in or larger version of the picture that you started with. And for technical reasons, in order for the tricks that I'm about to do to work properly, I'm going to duplicate every row and every column 5 times. So every pixel over here is being exchanged for a 5 by 5 grid of pixels over here, all of the same color. All right. Okay, start like that, and now I'm going to do a bunch of fills, all right? The first thing I'm going to do is fill with the white. So I start with this big picture here, and I'm going to fill with the white. What is that going to look like? It means everything becomes white except for the ones which used to be right next to a black, because a white can't be next to a black. So starting with this picture, I can fill with white, and now it looks like this. Everything looks white except for the ones which are right next to blacks, and the blacks didn't move. All right, I filled it with white. This is still a legal operation according to our definition of homotopies. Next, I'm gonna fill it with the light blue. That will change everything here to light blues, except for the ones which are right next to dark blues, which there are some dark blue little snakes here remaining. So I'm gonna now fill with the light blues. It looks like this. everything is light blue except for some of the things next to dark blues. And now actually we're almost done. For somewhat magical reasons, this always works. Next, if you look carefully at this picture, you will notice there are some pinks. There's one here, there's one here, there's one here and here. There are some pinks, but there is no pink next to another pink. And this is not a coincidence. So if you read the paper, you'll see we proved that after doing those two fills, it's impossible at this point to have a pink next to another pink. And what that means is I can do it one last fill with the reds. Everything will turn red except for what's next to the pinks. And it looks like this. Because those pinks were isolated and far apart from each other, they're far apart because we did that 5-fold subdivision. Now what you see here is just everything is red except for a bunch of these little islands. And those little islands are all T's and T inverses, all right? So what we proved this is the way that we proved our theorem. You do the subdivision and then you do these 3 fills one after another. This will always produce a picture which is a sum of T's and T inverses. And what that means is that this homotopy group is isomorphic to Z. The only pictures that you can get are ones which are equivalent to just doing some amount of T's and some amount of T inverses. That's why it's Z. And I think that'll do it. Thank you for your attention. Let me know if you got questions.